Like if I was high, I'd enjoy this class a whole lot more. All right, so I have no idea what day it is. I'll look at previous lectures when I label them. We're doing 6.2 and 6.3. 6.2 is on binomial probability distributions. In 6.3, it looks like the word Poisson, but there's an extra S. It's Poisson. The Poisson probability distribution. This makes me sad. I forgot that I was doing Poisson today. I normally bring in M&Ms and we do an M&M experiment. Oh well. Maybe we'll do it another time. So 6.2 binomial probability distributions. Binomial has the word bi in it. Bi means two. So binomial distributions or binomial probabilities are scenarios with only two outcomes. Or can be written as only two outcomes. Even if there's a lot more. Like previously we talked about roulette. Roulette has 38 outcomes, 38 different numbers. So that's 38 outcomes. But I can classify the events as A, red, and B, not red. And now I've broken it down into two categories, and that covers all of the outcomes. There's 18 outcomes in the red, and there's 20 outcomes in the not red. But it's down to two outcomes. So that's what I mean by we can break it down into, like, it may have more than two, but we can break it down into two. Sometimes it's just saying this or not this. Like rolling doubles or not rolling doubles. So binomial probability distributions, 4 requirements have to be met. First and foremost, there must be 2 mutually exclusive outcomes. That's the primary one, like the most important one. If you don't have, that's the easiest one to meet. The other 3 are all related to the experience, all related to trials or experiments from here on. I guess that is related to the trials or experiments, but like we need to have a fixed number of trials. So in terms of the roulette, this means spin the wheel 10 times is good. Good. Spin the wheel until I get 10 reds. That's bad. Because I could get 10 reds right away, or it could take me 100 spins to get 10 reds. So the number of times I have to do the experiment changes. See? Probabilities must remain fixed. Must not change. The roulette one's hard to give a good and bad example, but cards I can. How many red cards after 3 draws? And then if I do A with replacement, this is good. If I put the card back after each time I draw, the probability is the same each time. Without replacement is bad. If I just draw 3 cards, the probability of a red card on the second card and third card are different than the first card. That one kind of goes with the next one. They're like very related. D is the trials have to be independent. So one trial doesn't affect the next. If it did affect the next, the probability changes. So let's look at a few examples and see which ones meet the requirements, which ones don't. Some examples. I got a red cap on a black pen, which means I've got a red or black cap on a red pen, which means I have a red cap on a black pen somewhere here. Right here. There we go. Are these binomial. We're playing rock, paper, scissors. We're gonna play 5 games. And my random variable X will be the number of times I win. So A, are there 2 mutually exclusive outcomes? Well, if I'm playing rock, paper, scissors, I can either win, lose, or tie. But if the category is number of times I win, then my outcomes are win and not win. So not win would be lose or tie. So yes, that's met. Is there a fixed number of trials? We said we were playing 5 games. So yes. Is the probabilities are probabilities unchanging? Or probabilities fixed? Probability of winning. There's only one way to win out of the 3 outcomes. Probability of losing or not winning, not losing, but not winning is 2 out of 3. So yes, the probabilities are fixed. I think it's worth pointing out, note that they don't have to equal each other. And D, are the trials independent? This is a tricky one. Because a lot of people, when they play rock, paper, scissors, like if you lose, you kind of a lot of people change their shit up to beat whatever they lost to, which is foolish because anybody that's competing against them knows that's a common strategy. But a lot of people change their strategy if they win or lose. But whether or not you win or not is really independent because it's all related to what the other person throws. And you have no idea what they're going to throw. So yeah, they're independent. It may not seem like they're independent, but they are. So this would be a binomial distribution. What about, I want to see how homework completion rates affect test scores. So I go through grades. Until I find 10 people who completed their homework. Is this a binomial distribution? Well, there are two outcomes. Completed or not completed. That was A. B was fixed number of trials. This is no. It could be the first 10 students that I go through the roster for. It might be the last 10 students, or it might be sprinkled around. It might take me a while to find 10 students. So this one is not met. So this is not a binomial distribution. Any questions? I see people still writing. Does anyone need this longer still? Are you sure?
Yeah.
You look like you're writing. Can't trick me. All right, so if it's a binomial distribution, it has a mean and standard deviation. So the mean mu is n times p. And the standard deviation is, we're gonna do n times p, then we're gonna do 1 minus p, then we're gonna take the square root. We'll use that a little bit later. This is a probability distribution now. So guess what? This is the formula for probability of X. This is some good shit. We have n choose x. We're going to multiply that by p raised to the x power. And then we're going to raise it to multiply that by 1 minus p raised to the n minus x power. N is the total number of trials. X is the number of successes. And success here just means match to criteria. Like if you were counting the number of times you lose, that would be like a success. If you lost, that's a success. It's kind of a weird way of saying it, but that's the way it works. So total number of matches might be a better way of saying it. And P is the probability of success. This is an MFer. This is a bitch to do by hand. But hopefully you're not doing shit by hand. The only chapter you really had to do shit by hand for was chapter 5. We're not in chapter 5, we're in chapter 6. So we're gonna use Stat Crunch. Stat Crunch is stats calculators binomial. And the same things you need for the equation, you need these numbers for Stat Crunch. So we're going to look at an example. Everyone ready? Probably should have taken that. Solar is showing up to do an inspection on the house, see if I can put solar up on the house, and they're coming from 12 to 4. I bet that was them calling to say something. If those motherfuckers get there early, I'm gonna, like, I deliberately said 12 to 4 because I don't work from 12 to 4. I work from 4 to 7 and I work until 12, but 12 to 4, I don't work. All right. So example. Let's say, oh, I'm going to change this up from what I had before. 14% of car owners own 4 or more cars. I don't know if this is true. I'm making these numbers up. We sample 30 homes. See if they have 4 or more. So I'm checking 30 houses. There's only 30 houses. N is going to be 30. That means there's a fixed number of trials. The probability that the house has 4 or more cars is 14%. So P is 0.14. The probability is fixed. The houses should be independent. And as long as I'm checking different houses, there's no overlap, which means they're exclusive. Well, that's not what exclusive means. Either they end up in the group that has 4 or more, or they don't end up in the group that has 4 or more, and thus they're mutually exclusive. So that's my N and my P. What we're going to check is, what is the probability that exactly 5 have 4 or more cars? So we're gonna check a couple ones. We'll do that. We'll do the probability. We'll call that A. B is going to be the probability that less than 3 or 4 do. And then we'll check the probability that at least one house at lecture, but I'll do it when I get home at noon. All right, so exactly 5 means probability that X equals 5. What should I do for less than 4? What symbol represents less than? Yeah, the bracket, that's less than. The arrowhead bracket, I should say. So that's less than. And this one's greater than, for those of you that it's been a while. At least one house means 1 or more. So I could do X is greater than or equal to 1. We could also do that event complement thing, like the complement of this. is x equals 0. So we should be able to get the same thing if we do 1 minus the probability that x equals 0. These should be equal. All right, you guys ready to go look at it? You're gonna kind of like how this does it in StatCrunch. This is pretty cool. So go into your homework, open up StatCrunch. And we're gonna go to stats, calculators, binomial. It's the second one on the list. It asks you for n and p, and then what we're gonna do with x. N was 30. P was 0.14. And the first one we had was x equals 5. Notice there's a drop-down menu right here. They've got less than or equal to at the top, greater than or equal to, less than, greater than, and flat out equal. So you're gonna have to pick the right sign along with the right value here, 5. They show the labels, and I don't know if you can see it well in class, but this column right here is red and the rest of them are black. And I can see it's the column between 4 and 6. The column between 4 and 6, that is my 5. So it's showing me which one it's doing. The probability that there are 5 houses that have 4 or more cars out of 30 is that 0.1765. I'm going to say 66 if I round to 4 decimal places. The next one we want to see was x was less than 4. So I'm going to change this to say less than, and I'm going to change that to say 4. Oh, there we go. Hit enter. And now I can see that the 0, the 1, the 2, and the 3 column are red, and the rest of them are black. And it gives me a value of 0.3785. And finally, we wanted probability that x was greater than or equal to 1. Look at that, 0.9892. I'm going to do the 1 minus probability that x equals 0. Let's take a look at x equals 0. 0.0108. We're going to come back and look at that in a second. So I wrote down what I had. I don't know about you, but I think I like looking at these in terms of percentages. So this is 17.66%. This is 37.85%. And let me do that 1 minus 0.0108. I get 0.9892 there, so those are a match, and that's 98.92%. I can find the mean and the standard deviation of this distribution, but it doesn't show it on StatCrunch. So to find the mean and standard deviation, we have to use a calculator. not SC. The mean was N times P, which was 30 times 0.14. Equals 4.2. The standard deviation was N times P times 1 minus P, then the square root. I've already done N times P, so that's the square root of 4.2. That's my N times P. Then 1 minus P is 1 minus 0.14. Times parentheses 1 minus 0.14. And then I take the square root and I get 1.9005. So this is that's one thing you can't do on Stack Crunch here, but it's just some simple calculator work. You got to memorize or know the formulas. I would do flashcards and stuff. I actually told the evening class tricked me, well, not tricked me, but talked me into allowing cheat sheet for the test. So there's going to be some form of cheat sheet for the test when it comes up. I'll let you guys know more next week. Okay. Just for the midterm. For the final, you gotta like tough it up. This actually has a couple more neat options. We can I'm gonna go back and do a couple more. Let's do the probability. That between 6 and 13 homes have 4 or more. Then I'm going to adapt that to say probability that between 16 or 6 and 13 inclusive have 4 or more. So if I write out the numbers 6 through 13, I got 6, 7, 8, 9, 10, 11, 12, 13. The numbers that are between 6 and 13 here are 7 to 12. Stack Crunch has a between option. I'm going to show it to you in a second, but the between option is stuck with the equality part there. You have to have that part. So I can't use 6 and 13 and just use less thans. I have to switch to 7 and 12 here to do that. Inclusive means include the 6 and 13. So on this one, I can do 6 is less than or equal to X, less than or equal to 13. All right, let's go look at this in StatCrunch. I still have the calculator up there. I'm going to use it. I'm going to click between. Well, I already clicked between. So the first one I wanted was 7 to 12. And I can see that doesn't include the 6, which is what I wanted. The probability here was 0.1164, which is 11.64%. And if I change it to 6 and 13, it makes it a little bit bigger. 0.2363 or 23.63%, actually quite a bit bigger. It doubled it. Fucking doubled it. Look at that madness. There's some nifty stuff that goes on with this, but I think we can explore it like using this calculator. So what if I set n to equal like 1,000? What shape would you describe that graph?
Bell?
Looks like a bell shape, right? What if I make the probability really, really low? Like I say, 0.01. Still looks fairly bell-shaped, right? What if I make it exactly half? 0.5. Oh, 0.5 is perfectly bell-shaped. That's for a large number of n. Like I could make it bigger and go down to 0.01 again. Oh, I got too many decimals there. In fact, there's so many lines there, it actually looks filled in. That's kind of neat. So like when n is large, this usually looks like a bell curve. The binomial distribution looks like a bell curve. Doesn't matter what the probability of success is. What happens? Let's go back down to 14. And let's change this to like 10. What shape does that look like? Looks skewed right, and like quite a bit skewed right, right? Let's make it a little higher. Let's go to 20. Still looks skewed right. What if I make the probability lower? It looks super skewed right. It's like a fucking landslide going to the right. What if I make it higher? What if I make it like 0.4? Looks close to bell curve, right? 0.5 looks like a bell curve. So what that means, if n is high, this is bell-shaped. It's a bell-shaped distribution. We want bell-shaped distributions. They're consistent. They always look the same. We can use the empirical rule on bell-shaped distributions. if n is low, well, this had some stuff going on. We saw that P, when P equals 0.5, it was still bell-shaped. So that was good. But when P was low, this was skewed right. What happens if P is high? What do you think is going to happen if n is low and then P is high? It's going to be, my intuition is skewed left. Low gave us right, high should give us skewed left. But let's go check. Make that 0.95. Yep, that's definitely skewed left. So yeah, it's skewed left. So we want bell-shaped. And so like if P doesn't give it to us, having the right P doesn't give it to us, we need to make N give it to us. And if P doesn't give it to us, we need to choose N so that it does. Choose N to be high enough that it does. We saw when we stuck in N equal to 1,000, didn't matter if we had really low, and alternatively that would be really high, it would still look bell-shaped. So how do we decide that? We want to meet the criteria, force N so or such that N times P times 1 minus P is greater than or equal to 10. That's just a formula you're going to need to memorize. Memorize that bad boy. It might help that this is N times P times 1 minus P. That was the inside of standard deviation. Which was square root of N times P times 1 minus P. In fact, when it's not the square root, this is actually called the variance. Variance is sigma squared. In this case would be N times P times 1 minus P. So this is the variance is greater than or equal to 10. But I don't think that's as helpful to remember because I don't know. I think you'll have an easier time with N times P times 1 minus P. Let's take a look at an specific example. Let's say P is 0.21. Nope, let's go with I don't know, 8, fuck it, 0.14. We just had it. Let's use 0.14. What is a good N? Well, we can solve for it. We have N times P times 1 minus P needs to be greater than or equal to 10. And I'm going to plug in 0.14 for P. I get 0.1204 times n is greater than or equal to 10. And to solve for n, we divide by that number in front on both sides. So n needs to be greater than 10 over 0.1204. That's not helpful. So this is 83.05647. So n needs to be greater than or equal to 84. Because you can't pick 83.05 ohms. Take a 5-minute break before we do 6.3. All right, we're going to take a look at 6.3 real quick. Six point P is on the Poisson distribution. It's like, sounds like poi, like soy sauce. Son, like, I don't know. Son. So requirements. The probability of 2 or more successes in a small enough interval is 0. So interval is like a distance, whether it's a length, like a physical distance, or like a distance over time, like how many seconds have elapsed. The point is, it's got to get down to where it can't be more than 1. If you make it, if you can get it small enough where there's at most, it can happen once, like answering the phone. You can't possibly answer the phone more than once per second. It just takes time to fucking answer, click, and have another call to come in. There's no way to get that where it's higher than once per second. Probability of success is the same for any 2 intervals of equal length. And the number of successes on any one interval or any interval is independent of the rest. And this means your intervals shouldn't overlap. like, let's say the interval is 2 minutes. Intervals are 2 minutes long. $12 to 12:02 and 12:02 to 12:04 are okay. $12 to 12:02 and 12:01 to 12:03 are not. They overlap. Now, let me give you the wonderful formula that is the Poisson distributions probability formula. P of x equals lambda t to the x over x factorial times e to the negative lambda t. That's pronounced lambda. And here it means the rate or average number of successes. E is the interval, and it's chose for t because it's often time. X is the number of successes. Of course, we're not using the formula. Not unless you're fucking batshit crazy. Stats, calculators, Poisson is the way to go. This requires x and mu of x. So I need to tell you what mu of x is. The mean is lambda times t. Standard deviation is pretty fucking easy. It's the square root of lambda times t, or the square root of the mean. Okay, you guys ready for an example? Nope, I see some people still writing. God damn it, I wish we had done M&M's first. My eye being sore fucked me up. I think I punched myself in the eye while I was sleeping. I don't know, I just woke up Monday morning and my eye just fucking hurt. And I kept going like this and like it just hurt to have open. And like driving and teaching, like fucking, I'm not a pirate. This isn't working for me. Because like I tried washing it out using, eye wash, rinse my eyes with water, nothing. Didn't fucking help. All right, let's look at the example. Everyone ready for the example now? All right. So the FDA sets a food action defect level. Abbreviated FADL. Nope, I said that backwards. It's food defect action level. Because they wanted their fucking initials in it. FDAL. And this is for various substances that inevitably end up in processed foods and drinks. Food and beverages. If it goes to a factory, there's some shit in it. It's not going to be pure. Shit happens. Dust falls in it. Bugs in the building. Goes through a grinder. You get some fucking bug parts. They have one for chocolate. Rather than telling you what it is, we're going to go look it up. I want you to see I'm not making this shit up. Give you guys a second to finish writing that. Food defect action level. FDA, top one on the list. Food defects level action or the handbook. Now it's a long list. You can see there's a bunch of stuff on it. Allspice, apple butter, canned apricots. You probably don't want to look at this shit, but we're going to do it for chocolate. So I'm going to do fine on chocolate. Chocolate and chocolate liqueur. The average is 60 or more insect fragments per 100 grams.
Oh, man.
Okay, so you guys see that, right? 60 more insect fragments per 100 grams.
It's just like a little bit of protein.
Is it usually grasshoppers or something like that?
I don't know why it would be grasshoppers in a building, but it might be
No,
grasshoppers.
There are like chocolate dipped grasshoppers that you can eat.
I remember they do grinding just to get the protein.
So it says 60 insect fragments per 100 grams. So like I can find a rate here a rate is, which is gonna be my lambda, is fragments per gram. So this will be 60 over 100 or 0.6 insect fragments per single gram. Now, a Hershey bar. A Hershey bar is 1.55 ounces. Just a good old block of chocolate. And if you convert this to grams, it is 43 grams. So, what is the probability that your Hershey bar has A, exactly 3 parts, 3 fragments. Fewer than 3. At least 3. Let's kick it up. Let's add some more. Let's do like at least 10, at least 20, at least 30. So Stack Crunch requires mu of x. Mu of x is lambda times t, which is going to be 0.6 fragments per gram times what? What's t here? Well, my probabilities are all in terms of fragments. My rate has fragments in grams in it, which means my grams need to go away. There's no grams listed in the probability. Grams need to go away. So if I multiply by the number of grams, mu of x is 0.6 times 43. And that is 25.8. That tells you something right there. The average Hershey bar has 25.8 grams. That's just, that doesn't sound good already. That's a good indication that it's gonna be pretty fucking high for some of these. And pretty low for some of these. So exactly 3 fragments. Let's write what each of these is. A means probability that X equals 3. B, what does fewer than 3 mean in terms of symbols? Is fewer less than or greater than? Less. At least 3 means 3 or more, which is X is greater than or equal to 3. And I had at least on the rest of these, so all of these are X is greater than or equal to the rest. These are what we're going to put in our Poisson calculator. To make you enjoy chocolate for the rest of your life.
So you know you got the 43 minus on the right,
Minus,
or what's that?
that should be at times.
Oh yeah, yeah. What's next in the parentheses?
0.6 from our fragments. And if we need it, we don't, but if you're asked to calculate the standard deviation, it's the square root of the mean, so square root of 25.8. Whatever that is. Okay, you guys ready? I see some people still writing. We're gonna go stats, calculators, Poisson. My mean was 25.8. And I wanted to start off with X equals 3. Zero point zero zero zero. How many fucking zeros are there? 7 zeros after the decimal point. Which is 2 times 10 to the negative 8. What about less than 3? Look, it starts at fucking 10. That's not a good sign. Less than 3 is times 10 to the negative 9. Holy shit. Greater than or equal to 3 means it's a sure fucking thing. 1. They don't even fucking say 0.999999999. It's just flat out fucking 1. At least 3 fragments are guaranteed in your fucking Hershey's bar or your money back. Wouldn't that be a fucking way to advertise that shit? Well, what about at least 10? 0.99986 or to 4 decimal places, 0.9999 to 4 decimal places. At least 10. 10 or higher. What about 20? At what point do I start going, okay, there's not that many. We're not there yet. 20 is 89656 or 8966. And if I were to say that in percentages, I would say approximately 90%. There's a 90% chance your candy bar, Hershey bar, has at least 20 insect parts. That might be a wing, it might be a leg, it might be an egg, like larva or some shit like that.
Oh.
Get some nice little protein in that motherfucker. It's all ground up, fucking cooked and all that. It's in there. You don't know it. You've never known it. Does anyone in here not eat chocolate? No one's allergic. Okay. Changes it, right? Kind of change. Not really. Just tune that shit out. Just block it out.
So this seems similar to pizza.
What?
Yeah, the same case in pizza apparently. It's like some bugs that get in.
In pizza? I guess depending on where it's being cooked at.
Says FDA is allowed in some cases. Like,
30.
perfectly safe, it says.
Oh, 30 gets low. 30 is only 22.84%. I don't know if that's low enough to make me smile, but. So when they tell you that chocolate isn't a good protein source, that's a lie. There's at least 20 fucking insect parts in it.
That's what makes it so addicting.
Right? That's the fucking cocaine part of it right there. It's got the hook. All right, I wanted to show you guys another one. I'm just going to start it for you. Question number 5 on 6.3. This is 6.3's homework. A lot of students struggle with the start of this. For the past 111 years, a certain state suffered 34 direct hits from a major hurricane, which is category 3 to 5. Assume this was typical and that the number of hits per year follows a Poisson distribution. In fact, most of these problems will tell you it follows a Poisson distribution. It says hits per year. That's going to help us figure out some stuff. So I'm going to write down the information they gave us on a piece of paper. And your numbers will vary when you get to 6.3, number 5. 6.3, number 5 is on hurricanes. And it gave me for the past 111 years, there were 34 direct hits. And it says number of hits per year follows a Poisson distribution. they're telling us the format of the rate. This is the format of the rate. And looks like T is in years. But our rate or lambda, well, we're doing an average, so we had a 111. Oops, nope, hits go on top. 34 hits over 111 years. If I do this in a calculator, I will get my lambda. 34 divided by 111. 0.306306. It keeps going. That can be written as 306 with a bar over it. And question A asks us, so students struggle with finding, like, tearing this question apart. What's it giving us? It's giving us the rate. Question A is, what is the probability that the state will not be hit? By any major hurricanes in a single year? Well, we know we're going to do this in StatCrunch. And StatCrunch requires us to have mu of x, which is lambda times t, which is going to be 0.306. I'm going to do 306 times, what's t here? What is the interval of time that's given? What does a single year mean? 1. T equals 1. So mu of x for that we're going to use in our Poisson calculator is 0.306. I'm going to do a bunch in there just because I want to make sure that the more you put in here, the more accurate your answer is. What does it mean that the state will not be hit? If we're measuring the number of hits per year, what does not hit mean? How many hits is that? 0. Not hit. Just stop and think about it. If you're wondering, like, how many hits is that? It's 0. So you're going to do the probability that x equals 0, and you're going to use mu of x equals, in my case, 0.306306. This problem is going to ask you a bunch of different, like, what about one hit? What about at least one hit? Shit like that. So it's going to ask you, like, to change it away from 0 a bunch of times, but most people are okay with that one. It's the not hit, like it doesn't fucking translate to 0 in a lot of people's heads. So not hit means you took 0 hits. This question will also say, is this unusual? There are several sub-steps that are gonna ask you if this is unusual. It is unusual if the probability of X equals whatever is less than 0.05. So if your number for, when you put it in the Poisson distribution and you get something that's less than 0.05 or less than 5 cents if you treated it as money, it's unusual. If it's higher than 5 cents, it's not unusual. I'll go plug it in a second, but after that, we'll be done. Actually, I'll go do that and I'll bring this picture back up in a second. For people that are rip roaring and ready to go. Get more help, stat crunch. I'm gonna go stats, calculators, Poisson. And I had 0.306, and I wanted equals 0. There's actually a pretty good chance they won't get hit by a hurricane. 0.73616,109 here. So that's how you go through and do this problem. That's all there is to it. If you need that up a little bit longer, write that out, go for it. But otherwise, lecture's done. Have a good weekend. Godspeed, GTFO.